Welcome to this presentation on the Automic Kubernetes, or K8s integration solution. We want to take this opportunity to explain what the integration brings to the Automic user community. In our efforts to develop new solutions to support cloud operations, the K8s integration plays a significant role in automating processes in containerized applications. All the capabilities usually available to conventional environments, systems, databases, ERPs, are extended to the containerized counterparts. The Automic K8s integration brings several key benefits to Kubernetes administrators. We'll explain what those benefits are in some level of detail. We'll provide some technical insights so that the integration components are clearly identified and the deployment sequence is understood. We'll focus on the configuration of the agents and the design of the two connection objects in the K8s jobs, which support several formats, process types, and even cluster types, regular clusters, and containerized software management systems. Finally, we'll run through a demo. Automic automation plays a central role in orchestrating operations across multiple environments, including Kubernetes, and synchronizes these processes with other non-containerized operations. For our customers, it's imperative that the level of automation capability be extended to Kubernetes clusters. We're able to configure process automation centrally in Automic, which can be conventional or containerized itself, and then trigger, monitor, and supervise all in one place. Vendors like Broadcom have a duty to meet the challenge of supporting containerized systems and make our workload processing services available to these platforms. The Automic K8s integration guarantees the same level of capability for containerized applications that customers have been enjoying for decades. The K8s integration meets the Kubernetes challenge by offering features that extend well beyond batch processing. You're able to handle multiple job formats, secured software configuration management systems, run commands in specific clusters, target certain pods, and rescale applications by adding or removing pods dynamically. Externalizing operations to a tool with a high degree of third-party integration means we can automate across both containerized and conventional applications. Using various agents and job object types, we can build sophisticated configurations involving multiple ERPs, multiple database packages, system processes like backups and data consolidation, file transfers, web services, irrespective of the type of environments. We start with two systems, the Automic Automation host and the agent system. The agent is configured with a simple INI file with the usual values: system, agent name, connection, TLS, and so forth. We start the agents with the UCXJ K8s Java commands. As soon as it connects to the engine, a number of template connection and job objects are created. One con to connect to the cluster, and the other to store authentication details to secure source code repository, say SVN. Let's assume we have 3 clusters and 1 secure SCM. These host applications in different namespaces. Automic job definitions target the namespace. For each cluster repository, we need to create a connection object in Automic. We use the con templates and duplicate it as many times as we have clusters, in this case 4. In the case of a conventional cluster, we also have several methods for authentication. In the case of the secure repository, we need an additional con object to authenticate. If the SCM is public, files are unprotected and the SCM connection can be left blank. Lastly, we create K8s jobs in Automic. We have 3 main process types: K8s, container scaling, and command type processes. The Automic job includes the single or dual connection objects based on the target system and the type of process. If the job is located in a repository, then we may need the SCM connection, depending on the level of security. We're able to retrieve the successive statuses and generate job reports. The procedure to deploy the K8s integration is as follows. First, we download the integration package from Marketplace. This package contains all the necessary elements. We unzip this package, which produces a directory containing the agents, the INI configuration files, and several other items like the start executable. We use the appropriate INI file for our specific platform. K8s is a standard Automic agents. It requires at least 4 values to be updated: agent name, Automic system, JCP connection and TLS port, and finally TLS certificates. When the agent is configured, we start it. New object templates are deployed. We create a K8s connection to every cluster requiring automation. For this, we use the template con objects, which we duplicate as needed. The con object references the cluster URL and stores the appropriate service account token for authentication. If we're running jobs from a secure SCM, then we create an SCM connection in which we store either an ID and password or a bearer token. If the SCM say GitHub is public, then the con object field in the job will be left blank. Finally, we use the various job templates to create the processes. Several types of K8s job formats are available: JSON, YAML, and files. We can also execute commands in a specific pod or run up or downscaling jobs. We install, configure, and start an agent to deploy the K8s integration. The agent is included in the K8s package, which we download from Marketplace. We unzip the package, which creates a file system, agent/K8s/bin, that contains the agent files. Based on the platform, we rename the agent configuration file ucxj/citx and set a minimum of 4 values: the agent name, the AE system name, the host name and port connection to AE's JCP, and finally the directory containing the TLS certificates. Finally, we start the agents by invoking the jar file via the Java commands. The agent connects to AE and deploys the object templates needed to support the integration, the cons or connection objects, and the various job types. Let's start with YAML, JSON, and file job definition since they're the most straightforward. You need a connection object to connect to the cluster and specify the namespace where the job is to execute. The two types, YAML and JSON, are the supported formats, and you simply copy and paste the code of the job in the job definition fields. The definition contains a job name, which should be reflected in the job name fields. If you wish to submit from a file, then this file must be present on the agent system. You indicate the path in the name. The second job type is execute command. This is the atomic equivalent of the kubectl exec-it command. You find two fields, label and field selector. These provide the ability to target specific pods by filtering on labels or fields. The kubectl get pods command with the show labels option produces the list of pods and fields, as well as all the labels assigned to those pods. You can type in the information in either fields, say metadata.name equal, and the name of the pod, or the label equal and the value name, and the command executes in all of the pods that match that label. The next type is the scale deployment job. This is really straightforward. You select the cluster, the namespace, and then browse the list of deployments, which is the list of applications currently running in the cluster, as well as the number of pods dedicated to each. You can easily increase or decrease this number by typing the desired value in the scale fields. Let's proceed with a demo of the con objects. We've created a folder dedicated to Kubernetes. You indicate the IP or DNS name of the cluster. We've already generated a service account token for the purposes of authentication, and it's been stored on the agent system. Ideally, you should be using a projected volume and mounted path. You also have the option of running processes from a source code management platform like GitHub. The method is the same. You create a K8s connection and reference the SCM's URL. The only difference lies in the login mechanism for the SCM, which cannot be stored in the base con object and requires a different type of con called SCM. It only stores authentication details. We have two authentication types: basic, which stores ID and password to the SCM, or authorization scheme, which relies on bearer tokens. We head to the folder that contains our jobs objects and create a new run jobs. Let's start with attributes, namely the Kubernetes agents. We enter the connection object to the appropriate cluster and click Browse to see if we can access the namespaces. For our purposes, we'll select the default namespace. We select the YAML format and paste the code of our job. The job has a name which should be reflected in the matching fields. We also check cleanup to make sure that the remaining traces of the job are eliminated. Finally, we set the activation to never so that we can manage our job and process monitoring. Obviously, this isn't something that we recommend in production, but you can use this for testing. We execute, supervise the job, and look at the engine and agent job reports. Let's take a quick look at the other two job definition types. Instead of submitting the job directly on the form, you can reference a file in the file system. This file must be present on the agent host. You can submit from a source code manager. There's very little difference. The process is essentially the same. The main distinction is the second con, where we specify the SCM con objects, which stores authentication. Note that the basic connection should reference the SCM URL and credentials to the Kubernetes cluster hosting the SCM.